Howdy folks, Mr. Hess back with another geometry lesson. Today we're going to be covering lesson 2.3, and the title of our lesson is writing proofs about segments. And to start things off here then, I want to talk about what it means to be congruent segments. Okay, as you can see here, congruent segments by definition have to have the same length. So if we have a couple of segments AB and CD here, and maybe the length of this one is 5 units long and this one is 5 units long as well, then we can say the two of these are congruent. The symbol for congruent is this right here. Okay, it's an equal sign like this. It's an equal sign, only it also has a tilde above it, I think is the name of that, is a tilde. But that additional little bit added on to the equal sign then gives us the symbol for congruent. Whereas there's the symbol, of course, for equals. Okay, so we can say then that segments are congruent if and only if they are equal in length. Okay, when I don't put a segment above it, that refers to the length of a segment. When we do put a segment above it, then it's read literally as segment AB. So this says segment AB is congruent to segment CD, which means then the length of AB is equal to the length of CD. All right, so let me try something next here. All right, so what I want to show you next is what's called the segment addition postulate. Okay, it's a postulate, meaning that we cannot prove this, but we know it to be true. It's never been false, you know. In fact, it's a very simple idea. If you look at my picture up here, I've got one overall segment split up into two smaller segments. And according to the segment addition postulate, this smaller segment AB, when added to BC right beside it, would give me a grand total of the full length of the segment AC. So AB plus BC equals AC. Okay, or in other words, if you plug in the actual values, you know, AB has a length of 2, BC has a length of 4, and then that means that the overall segment, of course, AC, has to have a length of 2 plus 4, or 6. Okay, very simple idea. But one of the hardest to prove, too, because it's a postulate. All right, so let's try a problem you might run into on your homework then that would involve this kind of stuff. And again, this is a very simple idea. Let's say that I've got a segment that looks like this. We're going to call it EFG. And suppose that I told you that that EF in this picture is a length of 8 and EG has a length of 15. So first of all, you should be able to find for us FG. Okay, so I'm gonna, first of all, I'm just gonna do some labeling on my picture here. EF is 8, so EF is that part right there. EG is 15. Now EG is the entire length, I notice. So this entire length along here is 15. And we want to find FG. Well, we're going to use the idea of the segment addition postulate here, but technically instead of adding, we're going to be doing some subtracting, because for right now, for example, I could call this X right here, and then I want you to see then that in my picture, This 8 plus that x, when we add them together, should equal the grand total of 15. So that's where I'm using the segment addition postulate, see? But to finish solving, do you see I have to subtract the 8 from the 15? So as you can see, that leaves me with 7 for this length. So there's FG. FG is 7. Okay, they might ask you a question like this even, too, on a problem like this. They might ask you, is segment EF congruent to segment FG? Well, EF was 8, FG was 7. They do not match. So if they do not have the same length, then they are not congruent. So are they congruent? No. No, they are not. Okay, so you'll have some problems like that you'll have assigned on your homework. Okay, and then the next problem I want to show you here is going to involve a little more algebra. Okay, on this next problem, you see we have a segment here that is broken up into a couple of smaller parts. We've got them labeled as 7x minus 17 and 2x plus 53. And they want to know what value of x will make segment LM be congruent to segment MN. So we want these to end up matching. We want them to be the same length. Okay, so if I want to know what value of x will do that, then why don't we just simply do this? Why don't we write an equation where we set these two equal to each other? So we're just going to say 7x minus 17 would equal 2x plus 53. And then we just need to solve for x. Okay, remember what I taught you about doing algebra. If you see a problem like this and you have multiple x's, you know, here I've got one on each side of the equation. Right here's the two halves of the equation. So if you have an x on both sides, remember I call that a sheriff bandit situation because they're on opposite sides. And in a sheriff bandit situation, remember the weaker one has got to go. So the 2x is going to go. I'm going to get rid of it by doing the opposite. That's how we get rid of things in algebra, is do the opposite. So whatever I do to one side, I have to do to the other. Okay, those are going to cancel out. That was the whole point of doing that. 7x minus 2x is 5x. I'm going to bring down the minus 17, bring down the equal sign, bring down the 53. Okay, at this point, I want to keep adding and subtracting as long as I can. I'm trying to get this x by itself. So right now I'm trying to get rid of the 5 and the 17. The only one that I can get rid of that would involve adding or subtracting is the minus 17. I do the opposite. I add 17. Whatever I do to one side, I got to do the other. So now I've got 5x equals 70. Okay, now I finally need to get rid of the 5. The 5 is currently being multiplied, so I'm going to divide. Whatever I do to one side, I got to do the other. And 5 goes into here, let's see, 14 times. So what value of x will make them be congruent? X equals 14 will. Now I wanted to show you real quickly. I noticed I skipped over a type of problem. If you look in your book here on page 57, there's an example number 2 here. And these are pretty easy problems. They mentioned that they're building this bookshelf here. And the bookshelf is made up of different boards that they put together to make it. And the list of the boards is right here. You have segments A, B, B, E. So AB is this top, see? AB. BE is then this right-hand side along here. EG is the next one. That's the bottom board. Then you got AG, which then completes our rectangle. The AG being this left side. Then there's also segments CH, DK, and FJ. CH, as you can see, is a board that runs across here, a little brace across there. DK is an even shorter one you can see running across right there. And then finally FJ. FJ is the one that's running vertically straight up right there. Okay, kind of stops short when it hits that board. Okay, and they want to know which of these boards would be the same length or congruent. So if you know anything about rectangles, you know the opposite sides should match. So I know this top AB would match the bottom EG. I also know then that the sides would match. So side AG along here would match side BE along here. Okay, the remaining segments that were left though, the CH, the DK, and the FJ, none of those have matching segments of the boards that make up the bookshelf. DK is this little segment across here. There are other segments in the picture that match its length, like, EF, but there's no board when we build this. There's no separate board EF. That's part of the full length EG. So that's why I'm saying DK doesn't have any matching segments, any matching boards, I should say, any matching boards in this bookshelf that it would match it. Same with FJ. You'll see FJ is that one that runs up here. The only thing that would have a chance at matching it would have been like GH or EC, but neither of those are full board lengths when they built this bookshelf. Okay? All right, the next thing I want to mention are some properties of segment congruence. Okay? And these properties I've already mentioned before. They were properties of equality. Okay, but this is kind of an offshoot of that, a subdivision of that, you might say. These are going to be properties then that involve congruence of segments. Now, like I said earlier, previously when I introduced these properties, we were doing properties of equality. So the statements would have looked like this. They would have said, according to the reflexive property of equality, you would say, oh yeah, this segment AB has the same length as itself. So length of AB equals length of AB. So the only change that we're doing now is instead of equality, we're changing it to congruence. But it's still going to involve segments. So this is going to become a congruent symbol now. And then we go ahead and put segment symbols above those. Because anytime you say that segments are congruent, you should be using the segment symbol as well as the congruent symbol. Okay? So again, symmetric property, the symmetric property of equality would have had an equal sign here and here. The only changes we made it into a congruent, and we're talking about segments. Okay? And remember, symmetric property is the one that allows you to take a statement and flip it around. So that's what they're doing here. They say, if AB is congruent to CD, then we could write it backwards and say CD is congruent to AB. Because if it has symmetry, then that means no matter if you flip it around one way or the other, it's still going to be the same on both sides. The transitive property. Again, we already talked about the transitive property for equality. Now we're just doing it for congruent segments. So that's why we have the congruent symbols again. The transitive property, if you remember right, though, is one that creates like a chain of events occurring, one after the other. So if you look here, we've got AB is congruent to CD, and then where this one left off, CD, that one begins. So that keeps that chain going. So now I say if AB is congruent to CD and CD is congruent to EF, then, have you figured it out yet? The last part of this would read, then the very first segment we named would be congruent to the very last segment we named. Because the segment CD here is really just a middleman. Okay, he's the one connecting the two ideas. So we've got that matching CD, and we're essentially eliminating the middleman and just saying then that AB would be congruent to EF. Okay, so that's the transitive property. And these three properties are really all you need when you're going to be working with proofs. And you have to involve some properties, and you want to use the congruent symbol here. Okay, then you're going to be using these properties in those proofs. Okay, speaking of which, let's go ahead and try one of those proofs. The proof I want to try here is the one right out of your textbook here on page 57. Excuse me. But if you look here, like any other proof, your first statement is going to be whatever you were given. So on this proof that we're doing, in the picture here, they indicated that AB is 12. And they also mentioned right here the length of AC is 24. Okay, so both of those bits of given information were listed right there in our first step. So we say that was given. All right, now the next step here has AB plus BC equals AC. And they want to know what's the reason that you would give for that. Okay, so if you look at your picture, what they're saying then is that this part right here, this AB part, if you were to add it on to the other part, BC, which is right beside it, then do you see that you're going to get a new bigger segment that would be called AC all the way across? So that's what they put here, see? The first half AB plus the second half BC equals the grand total AC. Okay, when they do that, when they're adding two smaller segments that are side by side in order to get a bigger, fuller, longer segment, then they are using this right here. They're using the segment addition postulate. Okay, so that's goes in this blank right here for our reason. They asked us what allows you to write that. It's the segment addition postulate. Okay, then the next step is entirely here. The whole thing's here. I just want to explain what they did. If you look, the givens, remember, said that AC was 24. And what do you know? AC occurs in step 2 right there. So they're going to take that AC out and they're going to replace it right here with a 24. Okay, they did it again with the AB. It said AB is 12 up here at the given. So what do you know? In step 2, there's an AB. So they replaced it right there with a 12. So when you replace these, when you put the 12 in and when you plug the 24 in, when you're plugging stuff in, you're doing what's called a substitution. All right, that gets us up to this fourth step. Now in the fourth step, they have BC equals 24 minus 12. And they want to know what allows us to write that. So what's the reason we would put here? If you see what they did here was in the previous step, we had a 12 over here with the BC. Okay, and then all of a sudden the BC is by itself. Okay, and then over here, I had a 24 by itself, but now all of a sudden there's a 24 minus a 12. So that 12 that was over here on the left is being moved over to the right. And when we do that in algebra, you're doing the opposite to get rid of it. So to get rid of this 12, they had to subtract it. So they're subtracting a 12 from here. They subtracted it from this side as well. See, 24 minus 12. So for step 4, the reason you would give is the subtraction property, because we're subtracting the same amount from both sides. Okay, and that gets us up to step 5 here. The entire steps here, I'm not real fond of their reason that they put here. They just say that they did some simplifying, and what it is right there. 24 minus 12 is in fact 12, so they were just simplifying it down to that. Normally, they would call that another substitution, because we know that 12 is equal to 24 minus 12. And if they're equal, you could substitute them in. But they just called it simplifying. And that's fine. You could do that too. Last step. Last step now says that AB is congruent to BC. And they have the reason here. They tell you that the reason is going to be definition of congruent segments. Okay, so, and they want to know which statements allow you to use this reason. Okay, now the definition of congruent segments normally in a proof is used just to either convert from saying these are congruent to saying they're equal, or vice versa. If they're already equal, then you could convert it to saying they're congruent. But in this case, we're using that definition because up here in step 1, it said AB was 12. And in step 5, it said BC is 12. So if AB is 12 and BC is 12, then AB and BC are congruent. Definition of congruent segments. Okay, so there's a rather simple proof. I'm going to show you another one here in a sec. All right, we've got a proof that I've put up here on the board. And you'll notice that there are some missing blanks yet that we need to fill in. Okay, there's a total of 4 steps. Okay, but every proof, remember, has a given statement and a prove statement. So make sure you pay attention to those from the get-go. In our given, we have that ABED is a square. And there's a second piece of given information as well. Notice the comma, and then they tell us that AB and BC are congruent. So in our picture, we could go ahead and mark AB and BC. Those two match. Okay, and then this is a square. And we're trying to prove that this segment DE down here is then going to be congruent to this segment BC over there. All right, so here we go. Now, every proof, the first step is always the same. All you have to do to get things started here is copy your given and say it's given. So all we have to do is fill in this blank here with the given information. So I'm just going to copy what I had up here. ABED is a square. And AB and BC are congruent. That was part of our given yet as well. I could probably squeeze that in right there. Okay, there's our step 1. Okay, step 2. Step 2, the reason they gave over here is that all sides of a square are equal in length. Okay, so we should be making some kind of statement over here then that we have in our square, you know, a couple of sides that are going to match here, because after all sides are equal. You could technically just list all 4 of them, you know, and say, okay, AB would be equal in length to BE, to ED, to DA. All four of those. But when I look at my proof a little further down, if I look ahead, one of the things that we're going to state is that AB and DE are congruent. And AB and DE just happen to be two of the sides of that square. So in the previous step, I'm going to say the same thing, only instead of congruent, we say that they have the same length. So I'm going to say that side AB and side DE are equal in measure or length. Okay, that's different than this one. See, the notation's a little different. Okay, but it will help lead into our next step anyways if I recognize that's the route they were going. Okay, so when I convert now from saying these are equal in length to the fact that they're congruent, there's a certain reason you should be giving over here. Okay, and this gets used quite a bit in proofs, so make sure you're paying attention right now. It's an easy step, I think, because if you notice, all they did was change from equals to congruent, or vice versa. If you go backwards, you go from congruent to equals, because the reason here is a definition that we're going to list. And definitions, remember, work forwards or backwards. Okay, so this is a definition that you would give for your reason. And have you figured out what definition that I'm talking about? It's the definition of congruent segments. Okay, if they're equal in length, then they're congruent. So it's the definition of congruent segments. And again, I want to emphasize that definition, since it's a definition, works forwards or backwards. So in a proof, if you go from saying equals to congruent, you're using that reason. Or if you even went backwards, if I go from congruent to equals, if I go that direction, I'm still using that same definition. All right, now, there's one last final step. It's what we were trying to prove. Oops. I left out a step. Let me add on there. I did something wrong here. There we go. I fixed it. I had mistakenly put down here a segment AB where it should have been a DE. Okay, but we're ready for that last step now. And if you look now at your previous steps, like back here in this given, I had that AB is congruent to BC. Okay, so if you look at that and look at that in combination with this idea, then we can actually generate this last one. Okay, you see how I had AB equals BC, but then AB also equals DE? So what we can do is we can perform what's called a substitution. So what I'm going to do here is a substitution using the substitution property. Okay, and I'll show you what I'm talking about. Since AB equals DE, since they're congruent, I could take this DE and I could put it in for that AB. Because again, DE is congruent to AB, so when I could put it in for that AB, and when I plug that in there, do you see now you'd have DE is congruent to BC? So that's what we're doing. We're using steps 1 and 3 together to do a substitution. Okay, so there you have then again a nice short 4-step proof that involves segments. Okay, you're going to have some on your homework as well. Do the best that you can. Just don't leave them blank, okay? give it your best guess. We're going to go over all our answers in class anyways. So if you leave it blank, then I have to assume you didn't try. So make sure you're trying on these problems. Okay, but that's all I got for this video today. And with time, I assure you with time you'll get better and better at these proofs. I know right now they probably seem a bit difficult, but the more you do them, the more you practice them, the better you'll get at them.